Hello everyone, welcome back to our lecture on computer programming for engineering applications. Okay, so before we dive into our lecture, let's do a quick recap of what we've covered before. So in programming, especially in language like C, we have different types of data that we work with. Think of these data types like different tools in a toolbox, just like how you might have a screwdriver, a wrench, and a hammer for different tasks. In programming, we have different data types for different kinds of numbers. So in C, we have these integer data types like integer, unsigned integer, short integer, and etc. These are like different size containers for storing whole numbers. You can imagine them as different size buckets for holding water, where each bucket can hold a different amount. Similarly, we have float types for dealing with numbers that have decimal points. Now, here's something interesting. Just like how we can write numbers in different way, like 10, 10.0, or even 10 to the exponent of 1, in programming we can write numbers in different languages. We can write them in decimal, octal, or hexadecimal. It's like having different ways to describe the same thing. Kind of like how you might describe a color as blue or navy. And in the world of programming, characters are like the building blocks of words and sentences, just like how letters make up words in a language. So when we want our brain to get a single character, we use C format specifier as our placeholder in printf and scanf. It's like saying, hey, we're dealing with a character here. Now, to help us work with characters even better, we have this handy header file called ctype.header. Think of it like a toolbox full of tools specifically designed for handling characters. So inside this toolbox, we've got functions like putchar, which prints out a single character, and getchar, which gets a single character from input. Then we've got functions like toUpper and toLower, which helps us convert characters to uppercase or lowercase. It's like having tools that can change the shape or size of our building blocks. Now, when it comes to dealing with different types of data, like converting from one type to another, there are some rules to follow. It's like when you want to convert one currency to another, there are specific steps that you need to take. One way to make sure the conversion happens just the way you want is by using something called casting. So casting is like giving a clear instruction to the computer saying, hey, make sure you convert this exactly how I tell you to. It's like having a translator who ensures your message gets across accurately. So remember, when it comes to characters and data types, we've got placeholders, tools, and casting to help us navigate through the programming C's. And in this lecture, we're going to talk about arrays. Alright, by the end of this session, you'll understand arrays like a pro. So, what are arrays? So think of them like shelves in a library. Each shelf can hold multiple books, right? Well, in programming, arrays are like shelves, but instead of holding books, they hold pieces of data, like numbers or words. So first up, we're going to learn how to use arrays to organize our data. We'll write programs that use what we call aggregate variables, which is just a fancy term for variables that hold multiple pieces of data together. Kind of like a backpack, your backpack holding all your school supplies. And then we'll tackle one-dimensional arrays. Picture this. You have a row of boxes and each box can hold something different, like shoes, socks, or toys. Similarly, a one-dimensional array is like a row of boxes in programming, where each box holds a single piece of data. We'll learn how to initialize these arrays, which is like putting stuff into each box, and how to access specific items using something called subscripting, which is like labeling each box with numbers so you can find it easily. Next, we'll level up and explore arrays with more dimensions. Now, This might sound fancy, but it's just like adding more layers to our shelves. So instead of having just one row of boxes, we'll have multiple rows stacked on top of each other, like shelves within shelves or box within boxes. So it's like about organizing our data in a way that makes sense and helps us work more efficiently. And along the way, we'll practice using designated initializer, which is like having a special tag on each box telling us exactly what goes inside. This way we can set up our arrays with the right data from the get-go. Alright, let's talk about two types of variables, scalar and aggregate. Don't worry, we'll keep it simple. So far we've been working with scalar variables. Think of them like single serving cups. They're great for holding just one thing at a time, like your morning coffee or your snack, I don't know. And programming, scalar variables do the same. They hold a single piece of data, whether it's a number, a letter, or something else. But there's more. There's also aggregate variables. These are like baskets that can hold a bunch of stuffs all at once. So instead of just one item, they can store collections of values, kind of like a picnic basket filled with sandwiches, fruits, cheeses, drinks. And now in the world of C programming, we have two main types of aggregate variables, which is arrays and structures. And today our focus is on arrays, which are super cool because they're like a bookshelves, and you can stack multiple items on each shelf, making it easy to organize and access them. And today we're going to one-dimensional arrays, which are like single rows of shelves, and they're simpler to manage and understand compared to multi-dimensional arrays, which we'll discuss later. Alright, let's zoom in on one-dimensional arrays. Think of them like a line of boxes. So each box holds a single item, like a toy or snack. Now in programming, these boxes are called elements, and they all have the same type of data inside. So it's like having a line of lunch boxes, and each box contains a sandwich with different sizes. Now what's cool about arrays is that you can pick out each item individually, just like choosing a specific box from our line of lunch boxes. You don't have to grab the whole line, you can just reach for the one you want. So when we talk about one-dimensional array, we're basically talking about a single row or column of these boxes. It's like arranging all our lunch boxes side by side in a neat line. So each box has its own place, making it easy to find and use. So imagine yourself building a Lego tower. Before you start building the Lego tower, you need to decide what kind of Legos you're using and how many you'll need. Similarly, when we declare an array in programming, we're basically saying, hey, computer, get ready to store this type of data and I'll tell you how many pieces you'll need. And so let's break it down. When we declare an array, we first specify the type of data our array will hold. It's like telling the computer whether we are using regular Legos or special shaped ones, and then we tell it how many elements or pieces our array will have. It's like saying we need 10 regular Legos to build our tower. So for example, if one array named A that can hold 10 integers, we declare it like this: integer A square bracket 10. It's like saying, hey computer, get ready to hold 10 integers in array A. Also, there is this trick. Instead of typing out the number of elements every time, we can use a macro, which is like a shortcut. It's like having a label maker to quickly mark all your boxes. So we define a macro called n and set it to 10 using define n10. Then whenever we declare an array, we can use n instead of typing out the number every time. So integer a square bracket n is like saying hey, using hey computer, make an array a with n pieces where n equals 10. Alright, let's learn how to grab exactly what we need from our arrays. It's like reaching into our Lego tower and picking a specific piece to work with. So when we want to access an element in an array, it's as simple as telling the computer which piece we want. We do this by writing the name of the array followed by number in a square bracket. It's like telling the computer, hey, give me the piece at position number 3, for example. This process is called subscripting or indexing the array. It's like labeling each piece in our Lego tower with a number so we can find them easily. And now here's the fun fact. So when we're dealing with arrays, we start counting from 0, not 1. So if we have an array of length 10, the pieces are numbered from 0 to 1, not 1 to 10. So it's like starting our Lego tower from the ground floor with the first piece being the number 0. For example, if we have an array named A with 10 pieces, we access the first piece using A square bracket 0, the second piece using A square bracket 1, and so on, all the way up to A square bracket 9. It's like saying, hey computer, give me the piece at position 0, then piece at position 1, and so on until 9. Alright, now that we know how to pick out specific pieces from our array, let's see what cool stuff we can do with them. It's like having a toolbox full of tools. We can use them to build all sorts of amazing things. So when we use expressions like a square bracket I, where a is our array name and I is the position of the piece we want, it's not just a way to grab data. It's like having a magic wand that turns our array elements into powerful variables. So these expressions, by the way, are called ELF values, which is just a fancy way of saying they can be assigned values, just like any regular variables. So for example, we can assign values to array elements just like we'd put different things on our Lego tower. So a square bracket 0 equal to 1 is like saying, hey, put the number 1 into the first piece of our tower. We can also print out the value of an array element using printf, just like showing off our Lego to our friends. So printf from a specifier d a square bracket 5 is like saying, hey, tell everyone what's in the 6th piece of our tower. And hey, we can even do cool stuff like incrementing the value of an array element, just like adding more layers to our Lego tower. So increment a square bracket I is like saying, hey, add one more to the value of the piece at the position I in our array, in our tower. So in general, each element of our array behaves just like a regular variable of the same type. So whether it's adding, subtracting, or just showing off, we can treat our array elements just like any other variable in our program. Alright, now that we know how to work with individual pieces in our array, let's talk about how we can use loops to tackle our arrays as a whole. It's like having a conveyor belt that helps us sort through all the items in our Lego tower one by one. So imagine we have a big pile of Lego pieces in front of us and we want to do something with each of them. That's where loop comes in handy. They're like hands that pick up each piece one after the other and do something with it. So for example, let's say we want to clear out all the pieces in our tower. We can use loop to go through each piece and set it to 0. It's like having a broom that sweeps through our tower and clears out all the clutter. So the first code is like saying, hey, can you loop through every piece in our tower and set it to 0? And now let's say we want to fill our tower with new pieces. We can use another loop to read data into each piece. It's like having a conveyor belt that brings new pieces to us and we put them into our tower one by one. So the second code is like saying, hey, loop through every piece in our tower and fill it with new data. And hey, maybe we want to find the total value of all the pieces in our tower. It's easy. We can just use another loop to go through each piece and add up their values. It's like having a calculator that adds up all the numbers for us. So third code is like saying, hey, please loop through every piece in our tower and add up all of their values. So in each case that I've showed before, our loops helps us handle our array efficiently, piece by piece. Alright, now that we are already working with arrays and loops, it's time to talk about something important, staying within the bounds of our array. It's like making sure we don't step outside the lines when coloring a picture book. It keeps everything neat and tidy. So in programming, C doesn't hold our hand when it comes to checking if you're accessing file pieces in our array. So if we try to grab a piece that's not there, it's like reaching for a cookie in an empty jar. We're left with nothing but disappointment. Here's a common mistake. So forgetting that our array starts at index 0, not 1. So it's like thinking the first step on the stairs is number 1, when really it's number 0. So if we have an array with 10 places, they're numbered from 0 to 9, not 1 to 10. So now here's where the things get tricky. Let's say we have this innocent looking loop that starts from 1 and goes up to 10, trying to set each piece in our array to 0. So it's like trying to paint the 10 step on a staircase that only has 9 steps. So some compilers might not catch this mistake and our program could end up in an infinite loop. So it's like stepping forever on that imaginary 10th step, never reaching the end. So it's important to double check our array bounds and make sure our loop starts from 0 and go up to the length of our array minus 1. It's like staying on the right path and avoiding getting lost. Okay, now that we're comfortable with arrays and subscripting, let's level up and see what else we can do with them. So remember how we could access array elements using simple numbers? We can also use more complex expressions to access our array pieces. For example, in the expression with the orange color, we're not just using a single number to access our array piece. We are using an expression with addition and multiplication. So the code in orange is like saying, hey, find the piece at position I plus j times 10 and set it to 0. But wait, there's more. So our expressions can even have side effects, just like unexpected things when we're running a program. So take a look at the loop with the red color. Here we are not only setting our array piece to 0, but we are also increasing the value of I with each iterations. So the issue with this code is that it may lead to undefined behavior. In the expression a square bracket I increment equals to 0, the order of evaluation is not guaranteed by the C standards. This means that it's not guaranteed whether I will be incremented before or after its current value is used as an index to access the array A. So it's generally better to separate the increment operation from the array access and put the I increment after we access the element of A. Here in this slide we see another example of the side effect. So we have a loop where we're setting values in one array based on values in another array. It's like copying notes from one notebook to another, but the problem is our expression for accessing array elements has a side effect. It's like trying to copy notes while also erasing them at the same time. So for example, let's take a look at the loop in orange. Here we're not only setting values in array A based on values in array B, we're also increasing the value of I with each iteration. So these code have the same problem with the one in our previous slide. And the solution is simple. We just have to remove the increment from the subscript and put it somewhere else. By avoiding side effects in our array subscripting, we keep our code clear, predictable, and safe. Alright, now let's take a look at this interesting program called reverse.c. So it flips a series of numbers, just like when we're flipping a pancake in a pan. So here's how it works. First, the program asks the users to enter a series of numbers. So it's like asking someone to write down a list of ingredients for a recipe. So the user might type in something like the one in the slide. And now the program takes these numbers and stores them in an array, and each number gets its own spot in the array. And next, the program goes through the array backwards, just like flipping the pancake over. So it starts from the end of the array and works its way back to the beginning. With each step, it grabs a number and prints it out. So when we run the program, we see the numbers in reverse order. It's like reading a list of ingredients backwards from the last to the first. So instead of seeing the number in red, we see the number in orange when we run the program. Alright, let's see behind the scene of the reverse.c program and see how it works its magic to flip our series of numbers. So first off, we have some lines at the beginning of the program that set the stage. It's like setting up our kitchen before we start cooking. So we include a special ingredient called started input output header, which helps us communicate with the user. And then we define a constant called n to represent the number of numbers we want to reverse. It's like setting number of pancakes we're flipping in our pan. And now let's dive into the main part of the program, where all the actions happens. So we start by declaring an array called A to store our numbers, and we also declare a variable I to help us keep track of our position in the array. And next we ask the user to enter n numbers, just like asking for ingredients. And we use a loop to go through each number and store it in our array A. And once we have all our numbers stored in the array, it's time to flip them around. We use another loop here to print out the numbers in reverse order. Now let's see what happened when we run the program. Alright, next let's talk about how we can give our arrays a head start by setting their initial values. So it's like preparing all the ingredients before starting to cook. So it will save our time and ensure everything's ready to go. So just like when we declare any other variable, we can also give our arrays an initial value right from the start. So it's like giving each slot in our array a specific ingredient before we even start cooking. Now, the most common way to do this is by using a list of constant expressions enclosed in braces and separated by commas. So it's like having a shopping list with all the ingredients we need for our recipe. And for example, let's say we have an array called A with 10 slots and we want to fill it with the numbers from 1 to 10. We can do this by initializing our array like the code in orange. It's like saying, hey computer, here's a list of numbers to fit into our array, starting from 1 and going up to 10. And just like that, our array is all set and ready to go with its initial values. So it's like having all our ingredients lined up in the counter, ready to be used in our dish. Next, let's talk about what happens when our initial list of ingredients isn't quite enough to fill up our array. So when we initialize an array with fewer values than its size, the remaining slots in the array are automatically filled with the value 0. So for example, let's say we have an array called A with 10 slots, but we only provide 6 initial values like the code in orange in the slides. Now what happens to the remaining 4 slots in our array? Well, they automatically get filled with zeros. It's like saying, hey computer, we've got enough elements for the first 6 slots, but for the rest just use 0. So the initial value for array A would be the one in red. It's like having some cookies with chocolate chips and some without, but at least every slot in our array has something in it. And just like that, even if we don't have enough ingredients to fill up our array completely, the computer makes sure that every slot is taken care of. Alright, let's talk about a super handy trick for setting all the values in our array to zeros. So using this feature, we can easily initialize an entire array to all zeros. It's like starting with a clean slate, ready to create whatever we want from scratch. So here's how it works. First, we declare our array just like usual, but instead of listing out all zeros one by one, we simply put a single 0 inside the braces. It's like saying, hey computer, I want all the slots in my array to be zeros. So for example, if we have an array called A with 10 slots, we can initialize it like the one in orange. It's like telling the computer, hey, fill up my array with zeros please. And just like that, the initial value of our array A will be the one in red in the slide. And now here's a little note. So it's not allowed to have an initializer that's completely empty, and it's also not allowed for an initializer to be longer than array it initialized. So it's like we are trying to bake a cookies without any dough, or we're trying to bake cookies without enough dough. It just doesn't work. So please remember this trick the next time you want to start fresh with all zeros in your array. And now let's talk about a quick shortcut we can use when initializing an array. So normally when we declare an array, we have to specify how many slots it has, like saying we're making a batch of 10 cookies. But guess what? If we provide an initializer with our array, we can skip mentioning the length altogether. So it's like telling the computer, hey, figure out how many slots you need based on the ingredients I'm giving you. So for example, let's say we want to make an array called A and fill it with the numbers from 1 to 10. So instead of saying integer A square bracket 10 with the elements, we can simply write the code, the one in orange in the slide. So it's like telling the computer, hey, here are numbers that I want in my array, figure out how many slots you need to fit them all. And just like that, the compiler uses the length of the initializer to determine how long the array should be. So whether we're making a batch of 10 cookies or a batch of 100 cookies, the computer takes care of everything for us. And next, let's talk about a smart trick called designated initializers, which helps us set only specific values we want in our array, leaving the rest to default values. So it's like customizing only certain parts of our recipe while letting the rest follow the standard instructions. So now imagine we have a big batch of cookies to bake, but we only want to add chocolate chips to a few of them. Using designated initializers, we can focus on those special cookies without worrying about the others. So here's how it works. So instead of listing out all the elements in our array and setting their values one by one, we can specify only the elements we want to customize. So it's like marking specific cookies with chocolate chips while leaving the rest plain dough. Now imagine we have a big batch of cookies, but we only want to add special toppings to a few of them, like I've said before. Designated initializers let us do just that by specifying exactly which slots in our array should have specific values, while the others follow the default instruction. So instead of listing out all the values in our array and setting their positions one by one, we can use square brackets with numbers inside them to indicate the positions we want to customize. So it's like marking specific cookies with special toppings while leaving the rest plain. So for example, let's revisit our array A with 15 slots. Instead of writing the entire array and setting specific values, we can do the orange code in the bottom of the slide, and it's like saying to the computer, hey computer, set the third slot to 29, the 10th slot to 7, and the 15th slot to 48. So each number inside the square brackets is called a designator, and it tells the computer exactly where to put each value. So it's like a giving direction to a friend who's decorating the cookies that we made. And just like that, with designated initializer, we can customize our arrays with ease and avoid the hassle of writing out every single value. So designated initializers not only help us set specific values in our arrays, but also make our code shorter and easier to understand. So with designated initializers, we can write our array initialization in any order we want. And next, let's see the rules behind designated initializers in C91. So when using designated initializers, there are a few important rules to keep in mind. The first one is that the designators, which are the numbers inside the square brackets, must be integer constant expressions. So it's like making sure that the elements we're adding to our array are always the same no matter what. And the second one is if the array we're initializing a specific length, each designator must be between 0 and n-1, where n is the length of the array, and it's like numbering the slots in our array starting from 0, and the last slot will always be one less than the total number of slots. And the third one is that if we omit the length of the array, a designator can be any non-negative number or integer. And the fourth one is that the compiler will figure out the length of the array based on the largest designator we've used. So for example, let's look at the array in the red one. Because the largest designator is 23, the compiler will deduce that the array should have 24 elements. And just like that, by following these rules, we can use designated initializers to customize our arrays with confidence and precision. And in this slide, we can see how we can mix and match different initialization techniques in C91. So in C91, we have the option to use both the older technique, where we list out values for each element one by one, and the newer technique, where we specify values for specific positions using designators. So for example, let's look at the array in orange. Here we are using both techniques to initialize our array C. It's like saying, hey computer, set the 5th slot to 3 and the 9th slot to 6, while the rest follow the default instructions. And now let's figure out the content of array C. We know that the first 3 slots are set to 5, 1, and 9 respectively, because we're using the older technique. And then the 5th slot is set to 3, followed by the 6th slot, 7, and 7th slot to 2, and finally the 9th slot to 6. And remaining slots are automatically filled with zeros as usual. And just like that, by mixing and matching initialization techniques, we can create arrays that suit our needs perfectly. And next, to demonstrate what we've learned, we have our new program called wrapdigit.c, which helps us check if a number contains any repeated digits. So here's how the program works. First, it asks the user to enter a number. Then the program goes to work examining each digit in the number to see if any appear more than once. So for example, let's say the user enters the number 28212 like in the slide, and the program will check each digit and notices that the digit 2 appears twice. It then prints repeated digits to let us know that there's a duplicate digit in the number. But if the user enters a number like 9357, where each digit is unique, the program prints no repeated digits. So in this program, we have an array of 10 Boolean values, which is like having a checklist with 10 boxes and one for each digit from 0 to 9. And it's our way of keeping track of which digits we've already seen in the number. So at the start, every element of this array called digit seen is set to false. So it's like starting with all checkboxes unchecked in our notebook. Now, when the program is given a number n to check for repeated digits, it starts examining each digit of n one at a time. So it's like inspecting each element in our array one by one. So as the program looks at each digit, it stores the current digit in a variable named digit. It's like writing down the element we are currently examining in our list. So imagine we're checking the number 28212. As the program inspects each digit, it marks the corresponding box in our checklist as true if it sees that digit for the first time. It's like checking off the list that we've had. And just like that, by keeping track of which digits we've already seen, the program can quickly spot if any digit appears more than once in the number. So in our program, the repdigit.c, we have this handy array called digit seen, which acts like our checklist. Like I've said before, it's like having a table with checkboxes to mark off any number that we've encountered. And now when the program examines a digit in the number, it checks the corresponding box in the digit seen array to see if it's true or false. And like I've said, it's like referring to our checklist to see if we've already used that list before, that information before. And if the box for that digit is already checked, meaning that digit seen square bracket digit is true, then the program knows that digit has appeared at least twice in the number. But if the box for that digit is unchecked, meaning that digit seen square bracket is false, then the program knows that the digit hasn't been seen before. And just like that, by keeping track of which digits have been seen before, the program can quickly determine if any digit appears more than once in the. Alright, let's take a closer look at the code that checks if a number contains any repeated digits. So in this code, we have a program that helps us check for repeated digits in a number. So the first program includes the important libraries, which is the standard Boolean, and then the standard input output. Standard Boolean is for using the Boolean values, the true and false, and standard input output is for input and output functions. And next, the program sets up an array called digit seen with 10 elements, which each of them initialize to false, and then the program prompts the user to enter a number. As the user enters the number, the program starts its investigation. It uses a while loop to examine each digit of the number one by one. So for each digit, the program calculates digit by taking the remainder when dividing n by 0. If the digit has already been seen before, meaning the digit seen at the index digit is true, the program stops its investigation because it has found a repeated digit. But if the digit hasn't been seen before, the program marks it as seen. It set the digit seen at the index digit to true and continues its investigation by dividing n by 10 to move to the next digit. And finally, the program checks if n is greater than 0. If it is, that means there is a repeated digit, and it prints repeated digit. Otherwise, it prints no repeated digit. Next, let's delve into the using of sizeof operator to measure the size of arrays. So imagine we have an array called A with 10 integers. Now, the sizeof operator helps us determine the total size of this array in bytes. If each integer in our array takes up 4 bytes of memory, then sizeof A will typically give us 4 bytes, because 10 integers multiplied by 4 bytes each. We can also use it to measure the size of individual elements in the array. For example, size of A at the index of 0 tells us how many bytes one integer in the array occupies. Now, here's the trick. If we want to know the length of our array, we can divide the total size of the array by the size of each element. So by using size of A divided by size of A at index 0, we get the length of our array. And just like that, sizeof helps us measure the size of arrays and their elements, giving us a clear picture of how much memory they occupy. And let's dive more into the using of sizeof operator with arrays in a loop. Now imagine we have an array called A. We want to empty each element. So how do we do this? We use a loop. Now, instead of manually counting how many elements we have in our array, we can use the sizeof operator. So the loop starts with I set to 0, and it continues as long as I is less than the total size of our array divided by the size of each element in the array. Now, what's clever about this approach is that we don't have to change anything in the loop if we decide to add or remove element from our array later on. So whether our array has 10 elements or 100 elements, this loop will efficiently clear out all the value inside the elements without us having to change a single line of code. And just like that, by using sizeof with arrays in a loop, we can quickly and easily perform tasks without worrying about the size of our arrays changing. And talking about the sizeof operator using arrays, and there might be some warning message that the compilers may produce. And in our case, some compilers might show a warning message when we use the expression j less than size of A divided by size of A at index 0 in a loop. So the reason for this warning is that the variable I probably has the type integer or a signed integer specifically, while sizeof produces a value of type size underscore t or an unsigned integer. Now, comparing a signed integer with an unsigned integer can sometimes be risky, but in this case it actually safe to do so. So even though the warning message might make us hesitate, we can rest assured that our code is still safe and sound. And just like that, by understanding why the warning message appears and knowing that it's safe to ignore it in this case, we can continue writing our code confidently, knowing that we're on the right track. And to avoid the warning I've talked in the previous slide, we can add a cast or casting, an instruction that tells the compiler how to interpret the data. So we cast size of A divided by size of A at index 0 to signed integer by putting integer in front of it. Then our loop looks like the code in the orange color, the one on the top. And Another trick is by defining a macro. So we define a macro called size that calculates the size of our array, and then we can use the code in purple in our loop. And just like that, by adding a cast or using a macro, we can avoid warning messages and make sure our codes run smoothly. Alright, so let us see our next program on this lecture, the interest.c, where we'll explore how money grows over time with different interest rates. So in this scenario, imagine yourself have $100 to invest. You want to see how much your money will grow over time with different interest rates. So you run the interest.c program, and it asks you for two things: the interest rate and the number of years you want to invest your money. And once you've provided these inputs, the program works at magic. And then voila, the program prints out a table showing value of your money at 1 year interval. But here's the twist: it doesn't just show the growth at one interest rate, it also shows how your money would grow at the next 4 higher rates. So this is all based on the assumption that the interest rate is a compounded once a year. And just like that, by running the interest.c program, you can explore different scenarios and see how your money blossoms over time. Here we can see the sample output of one session with interest.c program would look like. First, the program asks us to enter the interest rate. So it's like choosing speed at which your money grows. Let's say we pick 6%. And next, the program asks us how many years we want to invest our money for. Now let's choose 5 years. Now the program will run and it will print out a table for us. This table is like a map showing us the value of our money at different points in time at different interest rates. In the table, the first column represents the years, 1, 2, 3, 4, 5, and then we have the columns for different interest rates, 6%, 7%, etc. And finally, the numbers in the table shows us the value of our money at each intersection of year and interest rates. So, for example, in year 1, at an interest rate of 6, our $100 investment grows to 106. And as we move down the table, we see how our money blossoms over the years and with different interest rates. So by running the interest.c program, we can explore different scenarios and see how our investment flourish over time. So let me explain the workings behind the interest program using an analogy. So imagine yourself building a tower out of building blocks. So each row of blocks depends on the one below it. So similarly, in our program, the numbers in the second row of the table depends on the numbers in the first row. So it's like building the second row on top of the first. And to keep track of the numbers in the first row, we use an array. Think of this array as a shelf where we neatly arrange our building blocks or numbers. And each slot in the shelf holds one number from the first row. And now, once we've stored the first row in our array, we can start computing the values for the second row. And it's like using the blocks from the first row to build the second row on top of them. And we perform calculation based on the numbers in the array to fill in the values for the second row. And just like building a tower, this process can repeat it for the third and later rows. And we keep using the values stored in our array to compute and fill in the numbers for each subsequent row. So by using an array to store our initial values, we can efficiently compute and build each row of our table, just like stacking blocks to build a tower one row at a time. And our program works in layers, with each layer representing a different interest rate we want to calculate. The numbers in each layer correspond to the interest rate we are working with. And to manage these interest rates, we're using something called an array. It's like having a special shelf where we keep track of all the numbers, and once we sort the interest rate in our array, we use them to calculate values for each layer. And the cool part is that we can keep adding more layers using the numbers we've already stored to compute the next set of values. So by using this array, we efficiently manage our interest rates and compute values as needed. And now let's break down the code for our interest computing program. We'll keep it simple, we'll keep it step by step. And at the beginning, we have some set of stuff. We include a start input output library, which helps us with input and output. And then we define a couple of important things. We've got a constant called numRates that tells us how many interest rates we're dealing with. And there's another constant called initial balance, which is like saying we start with some amount in our investment. And now let's jump into the main part of our program. So we start by asking the user for two things, the interest rate and the number of years they want to invest their money. Once we've got that information, we're ready to start building our table. We print out the years heading, just like labeling the rows in our table. Then for each interest rate, we print out its percentage. It's like labeling the columns of our table. And next, we move on to the fun part. We're going to calculate how much money we'll have each year. It's like seeing how our money grows over time. We go through each year, and for each interest rate we do some math to figure out the new balance. And let's run this code. Let's see the output. And voila, we print out our table showing how much money we'll have each year at each interest rate. And that's it. Our program does all the heavy lifting for us, so we can sit back and watch our money grow. Next, let's jump to the multi-dimensional arrays. So it's like having a big table or grid where we can organize our data in rows and columns. Imagine you're in a library, so each shelf in the library is like a row in our table, and each book on the shelf is like a column. Now let's say we have a library with 5 shelves, and each shelf can hold 9 books. That's our multi-dimensional array, and in our programming language we call it a 2-dimensional array. The integer m, the index 5 and index 9 declaration tells us we're making grid with 5 rows and 9 columns. Just like in our library where we have 5 shelves and each shelf can hold 9 books. Now let's talk about the indexing. Just like you'd find a book on a specific shelf in the library, we can find data in our array using indexes. But remember, in programming we start counting from 0. So if we want to access the book on the 3rd shelf, second from the left, we'd use the indexes row 2, column 1. First number tells us the row, which is the shelf, and second number tells us the column, or the position on the shelf. So it's like having a map of our library where we can quickly find any book by knowing its shelf and its positions. And let's dive more into accessing elements in a multi-dimensional array. So imagine our library has shelves of books, and each shelf has different genres of books arranged in rows and columns. Now if we want to grab a specific book, we need to know which shelf or row and which position or column it's in. So if we're searching for a book on the 3rd shelf and the 2nd position, we'd say, hey, pass me the book from shelf 3 in position 2. So in programming it's pretty much the same. We use double square brackets to access elements in a 2-dimensional array. So for example, m square bracket I and square bracket j could translate to books, square bracket row, and square bracket column. Means we are selecting something from the row and the column j, row I and the column j in our array of books. Now, here's a common mistake to avoid. Some folks might be tempted to use a comma before row and column, like M square bracket I comma J. I think it's the same thing, but watch out. In programming, that comma is like a sneaky bug. It actually means something different and we end up selecting the wrong element. So remember, sticks to the M square bracket I and square bracket J, or in a book analogy, the books square bracket row and square bracket column. Now let's take a peek behind the scenes at how our two-dimensional array is stored in the computer's memory. So it's a bit like organizing books on a shelf in a library. So imagine each row in our two-dimensional array is like a shelf and each column is like a book. Now, just like you'd read a bookshelf from left to right, row by row, the computer stores our array in a similar way. So if we have a two-dimensional array called M, the computer lines up the rows one after the other, like sticking bookshelves next to each other. So it starts with the first row, then moves on to the second row and keeps going until it fills up all the rows. This way, when the computer needs to find something in our array, it can quickly locate it by following this neat, organized arrangement. So even though we see it as a table, the computer sees it as a series of neatly arranged shelves, making it easy to find whatever we are looking for. So let's dive more into how we can use nested for loops to work with multidimensional arrays. So it's like unpacking boxes within boxes to find what we need. So imagine you have a set of nested boxes, each containing a smaller boxes. These boxes represent our multidimensional array. Now let's say we want to set up an array to represent an identity matrix where all diagonal elements are 1 and the rest are 0. To accomplish this, we can use nested for loops. Think of it like opening one box at a time, and the outer loops controls the rows and the inner loop controls the columns. So for each row, we go through each column to set the appropriate value. If we're at a position where the row number equals the column number, we set the value to 1, indicating the diagonal. Otherwise, we set it to 0, representing the off-diagonal elements. This way, by systematically looping through each element of our array, we can efficiently initialize it to represent the identity matrix we want. So it's like unpacking boxes within boxes until we've arranged everything just the way we need it. So here's the implementation of the explanation that I've said before. Is how you can print identity matrix using multi-dimensional arrays. You can try this code on your own on your compiler and see what will be the output of this program. Now let's talk about how we can initialize a two-dimensional array. So it's like a filling in a grid with values, but we do it in a structured way. So imagine you have a grid of squares and you want to fill each square with a number. This grid would represent our two-dimensional array. Now, to initialize this array, we can use a set of nested curly braces, just like nesting boxes within boxes. And each pair of curly braces represents a row of our grid. And inside each pair of braces, we list the values for each column in that row. So it's like going row by row and filling in the values. For example, if we have a 5 by 9 grid, we'll have 5 pairs of curly braces, each containing 9 values representing the columns. And we start with the first row, then move on to the second row, and so on until we filled in all the rows. And by nesting these one-dimensional initializers within the larger set of curly braces, we can easily construct our two-dimensional array. And this approach works similarly for higher dimensional arrays too, making it a convenient way to initialize arrays of any dimension. So in programming, there are clever shortcuts to fill in arrays quickly, especially for arrays with many dimensions. So it's like finding a faster way to fill a large grid with numbers. Now, if we have a grid which represents our multi-dimensional array, and we want to fill it with values, we can use a shorthand method provided by C. This method allows us to use curly braces to initialize the array with values directly. However, if our initializer isn't large enough to fill the entire grid, C will automatically fill the remaining spaces with zeros. So it's like when we're pouring water into a glass, and if the glass isn't completely full, the rest of it is still considered empty. So for example, if we have a 5 by 9 grid and our initializer only contains value for the first 3 rows, C will automatically fill the last 2 rows with zeros. And this way our entire grid is still properly initialized, even if it didn't explicitly provide values for every element. So when we're initializing a multi-dimensional array, like our grid, each row is represented by a list of values inside curly braces. Now, imagine each row of our grid as a row of houses on a street. So if a house has fewer items or values than the other houses on the street, we need to ensure that the empty spaces inside the house are still accounted for. In programming, if an inner list isn't long enough to fill a row of our array, the remaining elements in that row are automatically initialized to 0. For instance, if our grid has 5 rows and 9 columns, and one of the houses on our street, which represent a row in our grid, doesn't have enough furniture or values, the empty rooms or spaces are still considered and filled with zeros. This will ensure that each house or row on our street, which is our grid, is fully represented, even if some houses have fewer items than the others. So imagine we're constructing a big puzzle. So each puzzle piece corresponds to a number in our grid. Now, let's say our puzzle have 5 rows and 9 columns, just like our grid. When we're putting together this puzzle, we don't necessarily need to put each puzzle piece in its own box before placing it on the table. Similarly, when initializing our grid on code, we can sometimes omit the inner braces, which represents the boxes for each row. So instead of neatly placing each puzzle piece in its own box, which represent each row, you can simply lay out all the pieces in a line, and the compiler, like a puzzle solver, will start filling in the rows of our grid piece by piece. Once it has enough pieces to fill one row, it moves on to the next row until our entire grid is complete. Okay, so when we talk about initializing a multi-dimensional array, it's like setting up multiple boxes inside one big box. Now, if we leave out smaller boxes inside, it's a bit risky, because if we miss one or add an extra one, it can mess up everything else inside the big box. But don't worry, there's a cool trick from C99 called Designated Initializer, which helps us work with these big boxes full of smaller boxes more easily. Now imagine we want to make a special type of box called a 2 times the identity matrix. It's like a magic square where the diagonal line is all ones and everything else is zeros. Here's how we do it. We create our big box named ident to hold our 2 times the matrix, and inside it we specify which smaller boxes to fill with numbers. So in this example, we say, hey, the box at position 0, 0 should have 1.0 inside, and the box at position 1, 1 should also have 1.0 inside. And guess what? The other boxes that we didn't mention, they automatically get filled with zeros. Okay, so you know how sometimes you have special set of things like your collection of stuffs that you want to make sure no one would touch? Well, imagine you want to make sure that collection stays exactly the same forever. That's where constant arrays come in. So Think of an array like a big box with compartments where you can keep different things. Now, if you want to make sure that nobody messes with the things inside those compartments, you can declare the whole array as constant. It's like putting a big sign on the box saying, hey, don't touch what's inside. It's staying exactly like this. So for example, let's say we have an array called hex chars that holds the characters for number 0 to 9 and letters A to F. And we can make sure this array stays the same by declaring it as a constant, like the code in a range. Now, once we declare this array as a constant, it means no sneaky program can come along and change any of those characters inside. They're locked in place just like your precious collection. So whenever you want something to stay exactly as it is, just add that const tag and your array will be safe and sound. Alright, let's talk about why it's awesome to declare your arrays as a constant. So it's like giving your array a shield that protects it from any unwanted changes. So first off, when declare an array as constant, you're basically telling the program, hey, hands off, this array isn't going to change ever. It's like putting a big sign on your collection of stops that say, do not touch. Now, here's where it gets really cool. So by marking your array as a constant, you're helping out the compiler, which is like the brain of your program. The compiler can now keep an eye out for any sneaky attempts to change your array when it's not supposed to. So it's like having a guardian watching over your stuff to make sure it stays safe and unchanged. And guess what? This constant thing isn't just for arrays. So it's like a tools you can put on other things too, like your integer or your float. But it's especially handy for arrays. So it's like having a special shield that protects your array from any unexpected changes. So when you want to make sure that your array stays exactly as it is and avoid any potential mishaps, just put the constant and you're good to go. Alright, so there's this rule in C89. It says that when you make an array, you have to tell the computer exactly how big it's going to be right from the start. So it's like when you're building a shelf, you need to know exactly how many stuffs it's going to hold before you start hammering the nails. But in C99, luckily things got a bit more flexible. Now, sometimes you don't have to decide the size of your array right away. So it's like having a shelf that can magically adjust its size depending on how many stuffs that you want to put on it. Now, let me show you a little program called reverse2.c. Now, what this little program does is ask you how many numbers you want to reverse. The same with our original reverse program. The only difference is based on your answer. It creates a special array that can fit exactly that many numbers. So it's like having an array that grows or shrinks depending on how many elements or how many stuffs you have. Like we've seen in our program before, in C99 we have something called variable length arrays, or VLAs for short. You can think of VLAs like shelves that adjust their size depending on how many things you want to put on them. Now, in our program reverse2.c, the array A is a perfect example of a VLA. So it's like having a shelf that grows or shrinks to fit exactly the right numbers of stuffs you have. So here's the best part. The size of a VLA is figured out by the computer while the program is running. So now, why do we even need these VLAs? Using VLAs, the program can figure out exactly how much space it needs for its data during the program runtime. But there's also a problem. If the programmer doesn't choose the right size for an array, it could cause problems. So if it's too big, it's like having an oversized box for just a few items. It will waste the memory, wasting space. And if it's too small, it's like trying to stuff all your items into a tiny box. It won't fit. So while VLAs are super handy for making sure you have exactly the right amount of space for your data, it's important to use them wisely to avoid any packing mishaps. So in C99, the length of a fairly doesn't have to be decided by just one number. You can use all sorts of fancy math to figure out how big your array should be. It's like when you're building a shelf, and instead of just saying, I want it to be 3 shelves high, you can say, let's make it 3 times the number of stuffs I have plus 5 shelves high. We can see these cool things work out by looking at the code in orange. See, you can use all sorts of cool expressions to determine the size of your array. Now, remember how we talk about arrays being like shelves? Well, just like regular arrays, fairlies can also have multiple shelves or dimensions. Now, let's talk about a couple of rules or restrictions for fairlies. First off, they cannot stick around forever. You cannot make a fairly that lasts forever and ever, or in fancy term, static storage duration. And secondly, you cannot give your fairly a fancy initial setup. You cannot say, hey, let's start the shelf with the specific items already on it. So we cannot initialize them at the start. So while fairlies give you a lot of flexibility in sizing your arrays, just remember these little rules to keep things running smoothly. Okay, I think that's all the materials that I have for today's lecture. So let's quickly recap what we've learned about arrays in C. So first off, arrays are like organized collections of stuff. They're handy when you have a bunch of similar things you want to keep together, like a row of integers, or maybe a row of toy soldiers. Now, the most common type of array we've talked about is one-dimensional array. So it's like the simple list of things, easy to understand and use. You can think of it as a single row of integers or single row of toy soldiers marching in line. And when we're working with arrays, we often use something called subscripting. So it's like putting labels on each integer, in each value, in each element in our row so we can easily find them later. Subscripting helps us access specific elements in the array. And remember those designated initializer we talked about? They're like special instruction for setting up our array exactly the way we want it, like arranging our toy soldiers or integer in a specific order right from the start. And lastly, arrays can have more than one dimension. So to sum it up, arrays are super useful for organizing our data, especially when we have lots of similar things to keep track of. Whether it's a simple list or a multi-dimensional grid, arrays help us keep our programming adventures nice and tidy. And that's a wrap on arrays in C. So you can access all of the codes that are shown in this video, and you can also access this slide on the description. There are also exercises that you can do in this video that you can do at home, and we'll later discuss it in the class if you have any question about the exercises. Nice to meet you all. I hope all of you have a great journey learning C programming language. See you.